Okay, now we're going to show illustrate the principle of rocket propulsion. Rocket propulsion is an example of the principle of momentum conservation and impulse. Basically, the concept of it is that you have some kind of rocket. It's going to release some kind of jet, gas, exhaust, something, and then that's going to propel the rocket forward. So the principle of momentum conservation comes here. The initial momentum of the rocket is 0. The momentum of the gas that's coming out, mass of the gas times velocity of the gas, velocity of exhaust, equals the mass of the rocket times the velocity of the rocket. Now the other thing is happening is as the rocket is losing gas, it's also losing part of its mass. So because it's losing part of its mass, this mass of the rocket is going down, the velocity of the rocket is going to expand even more. It's going to grow, it's going to increase as the mass goes down, okay? So when we derive the equation of that in class, we see that the thrust force on the rocket is equal to the velocity of the exhaust, how fast the exhaust is coming out, times the rate of change of how fast the gas is getting lost, okay? How fast the rocket is losing mass, dm dt we call that. This is in units of newtons, the thrust force. And then we derive the equation for the final velocity of the rocket. It's equal to velocity of the exhaust times natural log of the, this one should actually be initial mass. The initial mass of the rocket plus fuel divided by the final mass of the rocket plus fuel. Okay? So of course the initial mass of the rocket plus fuel is going to be larger than the final mass of the rocket plus fuel. When you take the natural log of that, you're going to get a number greater than 1. And so the final velocity of the rocket is a number greater than the velocity of the exhaust. Of course it helps if the velocity of the exhaust is also fast, like the jet is coming out quick. So what we have now is we have a cart like this, okay? We have a carbon dioxide canister in the can. This whole thing, I weighed it already. It has a mass of 384 grams. Now I'm going to weigh the mass of the carbon dioxide canister. Okay, over here. And it says 34.2. 34.2 grams. So collectively, the initial mass of the, if we call this our rocket, plus fuel, that includes the canister's own mass, plus the fuel that's in the canister, the gas, that would be the sum of the two, which would be 8, 11, 4, 18.2 grams. Okay, so let's see what's going to happen. And this is kind of a pretty fun lab because you get to put this here. The way that it works is I have a needle type thing here. All I have to do is go like this, poke the back of the canister, and the carbon dioxide comes out. Let's see. We hold this. That went pretty fast. Nice, huh? The gas came out, boom, it shot out. Okay? And you could hear that really loud noise. And it's even cold. When you hear feel the canister, the gas has come out and the carbon dioxide has turned into solid, from gas, and it's expanded and become cold. Let's measure the mass now. Twenty-four point eight grams. Okay? So the gas in there, since it was lost, the mass is lost. So what's the total mass now? 24.8 plus the 384. So mass final of rocket plus fuel is going to be 8, 10, 1, 4.8 grams. So what's the velocity of the rocket? In our case, the rocket or the cart. Okay, let's assume the initial velocity of the cart is 0. What's the velocity of the exhaust? That one is sort of an unknown here. Let's just assume for a second that the velocity of the exhaust is 1 meter per second. The gas is coming out 1 meter per second. Okay, then we take the ln of initial mass, 0.2 over 408.8. So let's see what we get here. Natural log of 418.2 divided by 408.8. Okay. 0.0227 meters per second. Okay. Which means 2.27 centimeters per second. Okay. So that means if that's true, this would have gone for every second interval, it would have gone 2 centimeters. Another second, 2 centimeters. Another second, 2 centimeters. Another second, 2 centimeters. Okay? To me, it feels like it went even faster. Okay? Actually, it did go faster because from here to there, how long did it take? Okay? From one side of the table to the other side. We could even go even further. We could take the distance from here to here. Okay? Measure how many seconds it takes. Okay? And approximate what our velocity was. So our velocity was faster than 2.27 meters per second. Actually, I feel like our velocity was roughly, the whole thing maybe took a second or less than a second. So our velocity was maybe close to 1 meter per second. You know. So what we could do is, we could do a lab situation here. We could calculate the final velocity experimentally, measure the distance, measure the time. We can calculate the final velocity. We can calculate the initial mass, final mass, and we could use that as a way to calculate the exhaust velocity of the gas. How fast is the gas going backwards? Okay. Of course, there's friction in the table, so we're not including that effect. But since it's on rollers, we can assume as if friction is minimized. Okay. So you can see this is a fun lab. You can be creative with this. You can either measure this or measure this and calculate them and compare them. So you can see how an exhaust going back can be used as a way to propel something forward. And this is the application of the conservation of momentum as applied to rockets and propulsion. Thank you.